All right. Welcome back, everyone. This is the second lecture, lecture one, on machine learning. It's also Halloween today, and this is the scariest thing I can think of. So it's perfect timing to learn more about machine learning. All right. Some quick administrative trivia, whatever this word is. I am still figuring out the YouTube thing, mostly just where to put it, not how to put it. So I'll probably make a decision next week and then upload lectures there. Again, I hope that you all come in person. You don't have to, especially if you're sick, stay home. I can't though. I don't have that excuse. Also, homework zero. You've had 1 week to play around with this. I've got 11 submissions already, so I think most people have figured that out. Raise your hand if you haven't yet finished the main part. I don't care about the extra credit. Okay, a couple people. So if you have any problems here, please let me know. I can help debug on your laptops or over email. I've already helped a couple people over email. But we do have a new homework every week. You just have 2 weeks to do it. So homework zero is due next week before lecture. And then homework one, I uploaded this morning and it will be due in 2 weeks. And then since homework one is the first homework where you're actually writing your own code, make sure that you are writing your own code and not asking someone else to write it for you. And then also I mentioned this is the scary lecture. What do I mean by that? I am afraid of math. I don't know about you. And machine learning turns out it's entirely math. So I am going to cover some of the math because it is really useful to know and it's important, but it is not required. There are no math prerequisites for this course. If you haven't taken multivariable calculus or linear algebra or probability and statistics, that's completely fine. For the most part, you can just import code and use it and it will work. When it doesn't work, it is really useful to know why it works and why it doesn't work. And that's where the math comes in. So if you understand the math, great. If you don't, that doesn't affect your grade in this course. It's only going to be part of the lectures. And like I said, the lectures aren't really important. It's where I introduce these ideas, but you should be learning mostly from these homework assignments where you're writing code. Any other administrative questions before we get started? Yep.
For the homework, do we get grading straight away or is it all done at the end?
I'll do it right away-ish. So like if one person is like sick and needs an extension, I'll wait until they submit. And then I'll usually grade it within a week or so. I was really bad at this last semester because I had too much travel, but I think I have very little travel so far this semester. So hopefully I'll be pretty quick with grading. And then I'll also show the solutions in lecture after the assignment is due, assuming everyone's submitted.
I don't somehow after us or just
No, anything, don't care. Moodle has a really nice feature where you can automatically download everything and it puts it in folders for everyone's name, so it doesn't matter. But thank you. It's a nice thought. Any other questions? Cool. All right, so what are we going to talk about today? I'll talk about some more concepts of machine learning, and then we'll jump into various supervised and unsupervised machine learning methods. So this lecture is mostly introducing the models themselves, and then in the homework assignment, you actually use the models and figure out their pros and cons. Okay, so just to check if people were paying attention last week, can anyone tell me the difference between AI and machine learning? I know we covered this. Yep.
AI is when a computer shows human-like
Mhm.
intelligence, and machine learning is just I have data, recognize patterns, and not see intelligence in it, just see train.
Kind of. So machine learning is a subset of AI. Machine learning is a form of intelligent like behavior. When I do machine learning, I'll show results in this lecture, but many of these look better than a human could label them. So machine learning is AI, but not all AI is machine learning. So what is the difference? What makes it a subset of machine learning or subset of AI? What does the learning mean? What are we learning from? I heard data very softly. Yeah.
Yeah, so machine learning is when machines learn from examples.
Yes, this guy read off the slides last week. Perfect. Yeah, so we're learning from examples, right? If we want to learn from examples, the first thing we need is examples. So it turns out actually the data itself is one of the most important parts of machine learning. This lecture, I'm not going to talk about the data at all, but next week, the next lecture is entirely about data. So we want to learn from examples. So the first thing we need is a data set. Now, data is a very generic term. Everything is data. All of you are data. All of you are made up of numbers. I could label you with your age. I could label you with many other numbers, but those aren't really who you are. They're all simplifications of that. So we need a specific kind of data. We need data curated for a specific purpose. So if I just give you a bunch of data, that's useless. If I give you a bunch of images of dogs, now we're talking about a data set. It's collected for a specific purpose. Most of the data sets that we will be using in this course have the following form. There's usually some kind of input and some kind of output. And we are trying to teach a model how to go from one to the other. So X is what we usually label our input. You can also call it the features that you are learning or doing pattern matching on. And this can be anything you want. It could be an image, it could be text. As long as it can be represented mathematically, it doesn't really matter. And then our output, our Y, or our target, the thing that we're trying to learn a mapping to, again, this could be anything you want. It could be a class label like cat, dog, mouse. It could be a mask where every pixel in the image has a specific label, or it could be things like bounding boxes, etc. So there's a lot of different things that we can predict with machine learning. This is one example. So we have an input. It is this cat. It might not look like it, but if you zoom in, it's actually just a bunch of numbers. So it's an image, it's RGB. It's just three matrices on top of each other, red, green, and blue. And then the number stored in there is how bright that color is. So that's a bunch of numbers. And our output, it doesn't really look like a number, but if I say there are three possible answers, cat, dog, and other, we can say cat is 0 and dog is 1 and other is 2. So now that's a number 2. So that seems fine. But here's another example. We have a sentence, a movie review, and then some sort of output score on a scale of 5. This is also perfectly valid as input. You can represent text as numbers. Your computer, everything is a number, and you can put text on your computer. Therefore, there's definitely a way to do that. There's many different ways, it turns out. And then our output could just be 4.5. So this is more of a regression problem. We're trying to predict a number, not a category. But both of those are completely valid inputs and outputs for a model. Now, here's where the math starts to come in. If I want to describe my data set in terms of math, this is usually how you'll see it. And this is kind of where the notation differs from different courses, different textbooks. But this is the notation that I learned from, so it's the notation you're going to learn as well. We have this little curly D to represent our data set, and this data set is the set, that's the curly braces, of tuples or pairs, X and Y, and there are n of them in total. So the data set is of length n. You could go from 0 to n minus 1, it doesn't really matter. So that is a data set. It is just a bunch of inputs and outputs. And it's not only here's 100 images and 100 labels, it's here's 100 image label pairs. So every input has an expected output. It has an answer. This process, what I've described so far, this is called supervised learning. So it's supervised because there is supervision. You have a correct answer. So you can take a model, for now we're just call it F. This can be any arbitrary function. We're going to be talking about machine learning and deep learning and all different kinds of fancy models, but all of them are just math. All of them are just functions. So you have some function F. It takes X as input and it maps to an output y. And here are a couple different ways of writing this, a visual representation as well. So this is probably 95% of this course is some kind of supervised learning, because this happens to be very powerful. There's a lot of things that can be represented with this form where you have some sort of input and you want an output. Whether you're writing a message to ChatGPT and ChatGPT is returning a message back, that is also an X and a Y. So if you can represent anything in terms of numbers, you can learn a function that maps between one thing and another. This is not the only type of learning out there. So what if we don't have an output Y? This is known as unsupervised learning because there is no correct answer given to the model. You can still learn a function f, and we'll talk about a few examples of this today to do unsupervised learning. You just can't predict a specific thing. So usually unsupervised learning is something like clustering. You're looking for things that are similar, even though you don't know what they are. So if I just give you a pile of images, as a human, you can look at these and say, these three look pretty close. These four also look similar. Even if you don't know what the image is, even if it's some weird species of bird you've never heard of, you can still cluster it, and so can a machine learning model. So we have machine learning with an output, an expected output, and machine learning without. If you can tell, there's a big white space in the middle, which means I'm probably going to fill something in there. So it turns out these are just two ends of the spectrum. There's all kinds of things in between that you can also do. So one is called semi-supervised learning. You see here we have an output, but it's not really the thing that we want. We really want to predict y. We have y prime, which is similar. This can come in many different forms. So for example, if I give you 1,000,000 images and only 1,000 of them have labels, but you do have 1,000,000, you could throw away the other 999,000, or you could still learn information from them even though they don't have labels. So that's one form of semi-supervised learning where you have partial labels. Another form that's really, really common in Earth observation and remote sensing is you have labels. You have a image that you would like to predict, but the resolution is different. So you have a really high resolution image, but really blurry labels of what the land surface represents. But you would really like to be able to train a model to predict high resolution information. So that would also be a form of semi-supervised learning. And then the other third one that's common is you have labels, but they're really not very good. So they're either labeled by someone who doesn't know what they're doing, or more commonly, they're labeled by someone else's machine learning. And machine learning, just like humans, makes mistakes. And so now you're dealing with, I have answers, but I can't always trust them. But I would really like to get as high accuracy as I can. So all of those fall under the category of semi-supervised learning. And then the final one is self-supervised learning. So here, we don't have any labels, but we do have our original data X. Can we still learn some sort of feature extraction pipeline from this data? This turns out to be really, really powerful, even though it looks simple and stupid, because this is what basically all modern foundation models are built on. So I'll give you an example, starting with text. Imagine you would like to train a model to translate between languages. So you have input in English and you would like to translate to German or vice versa. So what would you do? How would you train that? Well, you could take a bunch of documents and translate them yourself, and now there's a correct input and output. Here's the exact same thing written in English, the exact same thing in German, and you can train a model to go from one to the other. This works okay. This is how Google Translate worked 10 years ago, but it's not actually as flexible as we would like it to be because it doesn't actually understand anything about language itself. It just knows that this word means this word. It doesn't know what this word is. We would really like it to learn the rules of language, certain grammar structure, certain meaning. And also, it's really time consuming to sit there and manually translate everything. So if you want to learn from as much information as possible, why not download the entire internet, which is exactly what OpenAI did, take all of the text information, and then just randomly remove words, and then train a model to fill in the blank. So if I have a sentence, the blank today is sunny, you would fill in the blank and say it's probably weather or weather report, something like that. So you're learning the relationship between certain nouns and adjectives. So you can kind of fill in the blanks and learn. You can also do future predictions. So if I type in these three sentences or this paragraph, what is the next sentence that relates to this thing? And just by training on an augmented version of the data, so not the original data X, but a changed version X prime, to try to predict what was removed or what is missing, you can learn representations without having to label a single thing or translate a single thing. You can do the exact same thing with images. So imagine I take an image and I randomly blur out 75% of the image. You can still say, oh, I see an eye over here, therefore there's probably another eye over here, because most pictures are of mammals with two eyes. And you can learn representations, both low-level image features and high-level structural features from an image. So that's self-supervised learning. That's how all of your foundation models are trained, such as ChatGPT, such as Gemini. We're not really going to be doing much semi-supervised or self-supervised learning in this course, but if this is interesting to you, you could definitely do this for a final project. But this course will be 5% unsupervised, mostly just this lecture, and then 95% supervised every other lecture. If this representation doesn't make sense, I also made a meme that explains the exact same thing. So this is how I kind of think about supervised versus semi-supervised. Okay. The other thing that we care about is not just the input, but also the output. So what kind of tasks can you use machine learning to solve? Again, anything that can be represented as a number, you can make a prediction of that number. But there are different types of numbers that are used for different purposes. So at this point, there's mostly relatively low-level things that we can do with machine learning. So for example, we can predict a number. And this is literally a number. This number doesn't have any special meaning. This is a continuous scale, a real valued number. So imagine I want to predict temperature or wind speed. These would all be forms of regression. We're predicting a number. It could be multiple numbers. You could be predicting temperature for a large area, and every grid cell you want a temperature for that location. But these are all real numbers with real meaning, real physical meaning. Another thing that you can do is predict a category or label. So this is known as classification. You are taking your data and you are organizing it in some way. This is an image of a cat. This is an image of a dog. This is an image of something else. So that's 0, 1, and 2. But there's not really any meaning to those numbers. 1 is not larger than 0 or less than 2. It's just a different category. Cat is not less than or greater than dog, depending on your preference. And then finally, for a more unsupervised approach, even if we don't have a specific number that we can predict, we can still do something like clustering. So grouping together similar or separating dissimilar objects. Most of the models that I'm going to show you today can actually be used for all three of these, depending on how you train it and what kind of outputs it's making predictions of. You can also do this not only for a single input, but also at the level of an entire image. So if I do classification for every pixel in an image, we call that semantic segmentation. If I do regression for every pixel in an image, now we call that pixel-wise regression. And then if I do clustering for every pixel in an image, that could be something like quantization. You can technically do these things with machine learning models. They're not really that smart. They're kind of just doing every pixel independently without any information about any of the neighboring pixels. Um, when we get to deep learning, you'll see much more powerful ways of doing this that do take into account those spatial neighborhoods and learn higher level features. But for now, most of the things that we're going to be thinking about fit into regression, classification, or clustering. Any questions on any of this high level descriptions of machine learning?
This very important difference between self-supervised and unsupervised is because, if I understood correctly, both don't get labels.
Correct.
But how, like, self-supervised just changes the input, and unsupervised just creates categories and then.
Kind of. And this is also my definition. There are other definitions out there. There are some people who consider self-supervised learning to be a subset of unsupervised. So there's some people who would combine these two boxes, and that's completely fine. The way that I think about it is really what they're used for. So with unsupervised learning, our end goal is clustering. We basically want to do classification, but we don't know what they're called. So we're making categories, we're making buckets and putting stuff in it. And that's the end goal. We don't do anything else after we're done. With self-supervised learning, the goal is actually to learn about the data itself. So how is an image structured? What do images typically look like? What are the relationships between low-level features and high-level structure? So it's trying to actually basically learn how to extract features. It's not trying to solve any specific task that's useful to anyone. But I can take a model that is really good at extracting features and I can train it further on a smaller supervised learning data set. So for example, I can train a model on every image on the entire internet. And then I can say, here's 10 images of dogs, here's 10 images of cats. And it can say, oh, that's what those things are called. Now I understand. I've seen these a million times. Now I can label these things in the future. So this is a really powerful paradigm for building pre-trained models that know the features you want to extract, and then you can add in the supervision later with much, much smaller data sets. Can anyone shut the door back there? Thank you. Any other questions? This isn't really important. As long as you understand supervised and unsupervised, that's all we're really going to do in this class. But if you do see buzzwords like foundation model or self-supervision, that's what it's referring to. These kind of like fill in the blank games. You can do other things too. I can take an image and I can randomly flip it or rotate it. And to a human, these look exactly the same. But to a machine learning math model, all of the numbers are in completely different locations. And it looks like a very different image. But if you can train a model to say, yes, these two things that are flipped or rotated are actually the same image, they have a very similar representation, then it's learned what an image looks like.
Is that a way to like enlarge a data set and just have images and then flip all of
Yes.
them and have more data?
Yes, that's actually a really good point. So this is called data augmentation. If you have a very small data set, not enough to train a model, you can just randomly flip images, rotate images, crop images, distort images, change the color a little bit, and now your data set is 10 times bigger. So this is exactly what you're going to be doing in the second half of the course. We'll do this a lot for deep learning because deep learning is really, really data hungry. Machine learning is much less data hungry. So we don't really need to do this yet, but that's a good question. Okay. So supervised learning. Let's talk about supervised learning in more detail. So there's two families of models that you can build. There's parametric and non-parametric models. Parametric models are models with parameters. Non-parametric models, they actually might have parameters, but usually that's not the point. The thing that makes non-parametric models distinct is that as your data set gets bigger and bigger, by definition, your model also gets bigger and bigger. And I'll explain what that means later. Non-parametric models tend to require a lot more data than parametric models, but they're very flexible. They can learn a lot about the data regardless of the type of data that you're giving it. So I'll give you some more specific examples of this. So let's say I've got a bunch of data and it's been labeled. So you've got satellite images that have been labeled as forest or agriculture or water. And I would like to teach a computer how to use this information, these known labels, to make predictions in a new place. What's the simplest possible thing that we can do? Well, we can just say, this image looks like this image. This image is forest. This image is probably also forest, right? It's not too complicated. So this is actually a primitive machine learning model known as nearest neighbors. There's not really any learning involved here. It's actually more like memorization, right? You're basically saying, I've got this stack of images that I can look up anytime I need it. I know what these images mean. I can refer back to these and label new images that come in later. Again, this works better the more examples that you have. So there's many different types of trees, therefore there's many different types of forests. If you only have one or two pictures of forests, you're not going to be very good at a completely different forest on a different continent. What does this look like mathematically? It's a little bit ugly, but I'll explain what this means. So X is our new example input. So someone gives me a new picture of a new forest or agriculture or something. I don't know what yet, but that's my X. Xi is one of these examples from my data set. I know what it is. I can look it up. We are trying to find the input X. Given an input X, we are trying to find the example Xi that is most similar, that looks closest. There's many different ways that we can define similarity. For now, we're just going to do a 2-norm, aka Euclidean distance. So if I have a vector or a matrix, I can just say how close are these numbers in terms of like x squared plus y squared plus c squared, etc. So that's what these two bars means. We don't really care about doing the square root at the end because it's not really a distance. We don't really care about the magnitude of the distance. We just want the one that's closest. So we'll use a squared to get rid of the square root, less math for us to do. And we're looking for the thing that's closest. So we're looking for the value of I that minimizes this expression. So which data point in the data set looks closest to our new image, our new data point. And the yi of that data point will be our new predicted label. Now, if math doesn't speak to you, I can also explain this in pictures. What you get is something called a Voronoi diagram. So basically, let's say these are my inputs. And at the moment, it's just in two-dimensional space. So maybe this is latitude and longitude, and we're predicting land cover. But it doesn't have to be 2D. It can be 1 million dimensions. It doesn't really matter. So these are all of my labeled data points, the dots. And the color of that dot is the class that it belongs to. You could say red is urban and blue is natural landscape, something like that. Now, if I get a new data point that's not at one of these known locations, I can basically say, what's the closest data point I do know? That's what it is. So it's a very simple idea, but very powerful for building simple models very quickly.
We want to say that if I put a dot somewhere, we just want to see which point is closest, and that's where the colors come from.
Yes, that is exactly what we're talking about. So if I have a point right here, I would look at every single point in my data set. You might see why this is starting to get slow. We'll look at every single data point in my data set, measure the distance between this point and that point, and then find the one that's closest. This one, it's blue. My new point is blue. Done. Easy. We don't actually know what's there. We can only guess based on the nearest neighbor. So I've already mentioned this a little bit. These models work best when you have a lot of examples. If you want this to be quick, all of those examples need to be in your computer memory so that you can quickly look them up and compare them. So you have a finite amount of memory on your computer. It doesn't grow forever. These tend to require a lot of memory, which is not great. They're really fast for training because there is no training. You're just memorizing, right? You're just loading this information from disk. But they're really slow for inference. So if I want to make a prediction, I need to compare my new data point to every data point I've ever seen before, and that's slow. And then also the predictions tend to be quite noisy. So what do I mean by this? If we look at the image on the right, let's say I have a new data point in green, and I need to decide if this new data point belongs to the blue square class or the red triangle class. Which one should it be? There's actually a few different neighbors nearby. The closest one is red. But if I look a little bit farther, there's actually a lot of blue around as well. So it's not really clear which one we should use. There's many ways to extend nearest neighbors to improve the performance. So if we want to deal with this noise, we can use something called k nearest neighbors, where instead of looking at the closest point, you look at the k closest points, and then you take a mode of those. So for instance, if I set k equal to 1, the closest 1 point is this red triangle here, right? So it's red. If I set k equal to 3, 2 out of 3 are still red, so the prediction is still red. If I set k equal to 5, you look at the 5 nearest points, there's actually more blue than there is red, so this would switch over to blue. So the bigger your k, the smoother your predictions are, but you might have local inconsistencies or incorrectness. The smaller the k, the more noisy it is, but you also have the ability to learn very localized features. Which k should you choose? That completely depends on your data and how much you expect it to be smooth. So you've probably dealt with data before that has outliers. This is really good for ignoring outliers. You will always find one weird picture of a cat that kind of looks like a dog, even though it isn't. So that's what this is dealing with. You can probably guess k should usually be an odd number, because if you have 2 blue and 2 red, which one should you choose? This works for binary classification when there's only 2 possible classes. If you have 3 or 4, then it doesn't really matter which number you choose. You're going to have the possibility of a tie anyway. You can invent your own tiebreaker. It doesn't really matter how you do it. You can just say blue is more common, therefore, if it's a tie, I'll make it blue. Yeah, that's how to handle multiple classes. Basically, just do the same thing, but have some kind of tiebreaker in there. How would I use this idea for regression? I said that most of these models can be used for classification or regression. How would I use this exact same approach to predict a number instead of a label? Actually, not you. You've answered everything today. Somebody else. I have to let other people learn as well. I'm happy to wait all day. Yes. Yep. Yeah, exactly. So let's say each of these, instead of being a shape and a color, is a number. And every single one has a different number. Maybe their height. And it's a bunch of people, and depending on where they're from, some are taller and some are shorter. I want to predict the height of a new person based solely on where they're from in latitude and longitude. I can look at the nearest person, but again, that's really, really noisy. So I would probably want to look at more than one person. I would look at the nearest 3 people or the nearest 4 people, 5 people, or the nearest 3 or 4 countries. And I would say, what's the mean of all of those values? Mean is one way to do it. You can also do a weighted mean. So some of these points are closer than others. Maybe when you're doing regression, the closer one should matter more. So these are all different ways to extend this exact same approach for regression. But this is really the simplest possible machine learning model that you can think of. If it's similar to something I've seen before, maybe it's the same thing. There's not a lot of intelligence there, but there is some, and it can be learned from example. What is another way to do it? We said the previous way was not so great because you had to memorize every example you've ever seen before. Can we learn some kind of lower dimensional representation of the same information? This is called a decision tree. Again, if you want to make this really, really accurate, this kind of gets bigger and bigger with the more people you have, the more data points you have. But we can basically learn rules to classify data. So for instance, this is a real decision tree. You can predict someone's risk of heart attack very roughly based on a few different factors such as age, such as whether or not they smoke, such as body mass, etc. And you can say, given a new person, if I know their age, I can go down one of these three branches. If they're older, then they definitely have a higher risk of heart disease or heart attack, especially if they smoke as well. If they're overweight, that also increases their risk of heart attack. So there's ways to basically cluster data using these kind of rules and fit everyone into a certain class or again into a regression value. The user, when using a decision tree model, would specify a couple of different things. They would specify the tree depth. So how many questions, how many rows do I need to go down to get a final prediction? You'll notice that the tree does not have to be balanced. So some branches might be shorter than others. That's completely fine. And then you can also specify the tree width. So you'll notice that many of these, there are only two possible branches, but some can have three, some can have one, some can have 10. These are all hyperparameters that you as a user get to pick. You get to decide how big your tree is, and then the actual numbers, the values in that tree will be learned based on the data, based on the observations. And again, you can use this exact idea for regression. Here's a really poor example where you probably shouldn't use it, but you can. So imagine I have a bunch of numbers. You can kind of see there's something that looks like a sinusoid, but there's also a lot of outliers. Let's pretend, just for the sake of argument, that these outliers are actually real data points, and we do want to learn those values. So what I can do is I can create a decision tree, and I can say, based on the x-axis, I want to predict a y value. And these are the decision trees that it would learn. Again, this is not really working very well because as a human, we can see there's a sinusoidal pattern here. But the model does not know that, and it is trying its best to fit every single data point. So this is what happens when you have a little bit too much noise in your data. Any of you, I think there's some aerospace engineers, et cetera, in the course. This is the same thing if you've seen this before. So this is another way to think about it. Okay. Decision trees are simple. They're quite small. They fit into memory very well. It's just a rule-based system. There's not really that many possible options. But they tend to overfit, as in they memorize the data and they don't really learn the underlying distribution of the data. They just memorize individual data points. So what can we do to make our models more robust? Well, instead of using one tree, you can use many trees. So you can use something called a random forest. The idea with a random forest is we take not one decision tree, but multiple. And crucially, we train every decision tree on a different subset of the data. This is really nice because I can learn every tree in parallel, all at the same time. So it's a little bit quicker. Each tree itself is much smaller. And now all of a sudden, I have multiple trees that are making predictions, and I can do majority voting. There's actually a large family of machine learning research on this topic, where basically if you train a bunch of dumb models, it turns out they're usually better than one really smart model. There's different ways of combining them. These combinations are usually referred to as ensembles. And if you ever enter any kind of machine learning competition, the winner is almost always someone who just used a bunch of models and did majority voting. That usually tends to work better than one single model. Here's a specific application related to remote sensing. Let's say I have an image, in this case, a multispectral image of the Earth. There's a red channel, green channel, blue channel, near infrared, shortwave infrared, etc. And depending on the values in those different channels, we can classify each pixel in the image with a certain land cover type. So if I look only at band 4, if it's less than 46, it's probably water. It's just a really, really blue pixel, for instance. Um, if I if it's greater than 46, then I would look at band 3 and I would say, okay, is it more than 102? It's just a really, really white pixel. It's probably a cloud, etc. And you can do this for every pixel in your image. You can see the model itself. This is the whole thing. It's really small. It's just like 4 if statements, and then you're done. But an if statement is also AI. And if the values that it's learning are learned, it is technically machine learning. It's just very simple. Random forest in particular is probably one of the most popular models that people use in remote sensing just because of its simplicity and because it works with very little data. Nowadays, researchers are finally getting out of this random forest bucket they've been stuck in for so long, and they're starting to do deep learning. But deep learning really, really does require a lot more data. So if you don't have a lot of data, random forest is a great place to start. Any questions on any of these non-parametric models before we get into the more complicated ones? These should be relatively intuitive. I hope these examples are clear. You just look for similar things or you learn rules to organize the world. So parametric models, I mentioned these before. These are by definition parameter based. You have parameters. The number of parameters is unrelated to your data set size. So if you collect more data, you don't change anything. The model is still the same size. You're never going to run out of memory. They typically require less data because they're learning the underlying distribution of the data. But as a result, that makes a lot of assumptions. The most common assumption that you might see people talk about is this IID assumption. You're assuming that your data is independent and identically distributed. What that means is if I collect 100 data points and I get a new data point, that data point should not depend on the order of previous data points. And also, it has the same distribution as my previous data. So for instance, let's say we're trying to predict height. If I get 100 people and I arrange them by height, you should probably get some kind of a Gaussian distribution. Most people are average height. There's a smaller number of people who are really tall or really short. This is what most data looks like. Now, if I get a new person, as long as my first 100 people are diverse and representative, that new person should probably fit somewhere within this Gaussian curve. If every single person in my 100 people is like a really tall person, this new data point is not going to know where to fit into this model because we've never seen that example before. So you're assuming that your data has kind of a Gaussian distribution, but there's a lot of things that do follow that pattern. So when these conditions are met, these models work really, really well with very little data. The first one is probably one that you've actually seen before and you just didn't know it was machine learning. If you've ever heard of least squares, that is also known as linear regression, and that is a simple regression-based machine learning model. So for instance, I have this image on the right. If I get a new data point on the x-axis, I can predict what its y value will be just based on data points that I've seen before in red. I would predict it's the blue value. And it might be a little bit above or below that, but that's usually an accurate prediction, assuming that your data fits a linear distribution. I have linear in quotes because it technically doesn't have to be linear. You're learning something that is linear with respect to the parameters, which I'll show you in a second, not with respect to the data. So what do I mean by that? This is also known as ordinary least squares. You've probably done this before. This is a line of best fit. You've probably looked for patterns like this in data before. So let's start with the simplest equation that you learned when you were probably in high school or middle school, the equation for a line. So we have some sort of output f of x or y. We have some sort of input x, and then we have these two other things, a and b, or m and b, depending on what you learned in school. It doesn't really matter what you call them. These are the slope and the y-intercept, but collectively we refer to them as parameters. These are the things that we need to learn. Given a new x, if I know a good slope and a good y-intercept, I can predict the y. But I need to learn that slope and y-intercept based on the data that I've seen so far. And they're not all perfectly in a straight line. We need to learn some sort of middle ground that works well for predicting these things. Now, this is in 1 dimensions, but I can do the exact same thing in n dimensions, 2, 3, a million, etc. So if I want to convert this to a vector, let's say my input is a sentence or even an image, I can flatten my image into one really long vector, one sequence of numbers for every pixel. And instead of learning one slope, I can learn a different slope for every single value, every dimension. So I will rename all of these, and this is where things start to get confusing. F of x is y. I think you've seen that before. That's probably not very scary. A is now W1, and now it's a vector. And then B is just renamed to W2. So these W's, you can refer to them as weights or as parameters. Those are the same thing. Those are synonyms. If you haven't taken linear algebra, this might not mean anything to you, and that's completely fine. If you have W as a vector, X as a vector, Y and W2 are scalars, and you're doing a dot product between W1 and X, aka W1 transpose times X. So that's what this sentence means. You could also sit here and write this out and say Y equals W1 times X1 plus W2 times X2 plus W3 times X3 plus W4. That would be the same thing without the vector notation. But we're writing it this way to make it simpler. Now it works for any number of dimensions. We learned earlier that our data set is a bunch of data points, not just one. So can we simultaneously consider every single data point in our data set? Yes, of course, with any vector or matrix math. So now y is in bold because y is a vector. Y is every output for the entire data set. So now it's got n data points. It's one really long vector. I'm going to do another really tricky thing here. I'm going to take all of my x's, every x in the data set, each one is a vector. I'm going to put them as rows in a matrix. And I'm going to add one other column of ones. And then I'm going to make a W bold because it's a vector containing W1 and W2. Now, if you do the matrix multiplication of these things, you can basically say for each value of y, it's just that row of x dot product with the entire W. Now, this is why it becomes a parameterized model. If I add new rows to X, the size of Y changes, but the size of W does not. The size of W is fixed. It's just the number of input features for each data point. So this is really powerful. It works for any number of examples. you can train it on 100 and predict on 1,000 or vice versa. It would still work. The model itself is really just these W's, these parameters, these weights.
So when we have like y and x given, we first find out our w, and then afterwards, if we get a new x, we can use the w we found instead of y.
Exactly. So if you know your W, you can predict any Y given any X. Exactly. Okay. So the really tricky thing here is how do we get the W? This is not something that we're given. This is something we have to learn from the data. Machine learning is called machine learning, but it's actually just math. It's actually just optimization. We need to optimize our model to make the least amount of mistakes. So if you look at the image on the right, if I have an X as input and I predict a line in red, the goal is to minimize the amount of errors or mistakes that we make. So all of those dashed diagonal lines, dashed lines, those, if you add all of those up, that is the total amount of error or loss or mistake that we are making. And our goal is to make those small. So how do we optimize a function? If you've taken any optimization course before, you know that there's really only one answer. Does anyone know it? How do you optimize any function? You probably did this once and then you never did it again for the rest of your math career because you didn't know it was really important. So let's say I have a function. Too far. Let's say I have a function like this. Now, this is a little tricky because usually you have an X here and a Y here. I'm actually going to have a W here and an error here. So my goal is to learn W. I actually don't care about X and Y. I just want to learn a W that fits it well. So I can try many different values of W1, W2, etc. And different values of W will result in a different amount of error or loss. You'll also see a squiggly L very often. The amount of mistakes that you're making. Yep.
Steepest descent, maybe?
That's the second one. What's even simpler than that?
Find the first derivative.
Yep.
We'll get the tangent
Yep.
and we'll equate it to 0.
Exactly.
Yeah.
So that's the simplest method. That's probably the first thing you learned in calculus. The thing you said, steepest descent, gradient descent, that's the second thing when you realize this doesn't actually work all the time. But at the moment, this is very simple. We can do exactly that. We can take the derivative of this thing, the slope, and wherever this is equal to 0, that is our minimum. This is making some assumptions about this function. So this works really well for things like parabolas. And it turns out linear regression will always give you a parabola. But if I give you a function that looks like this, there's multiple different places where the gradient is 0, and you have no idea where the minimum is. And that's where you have to do something like gradient descent. This is usually where I start to lose people when I have a plot in like W error space. This is very different than the way that you typically think about math, but it's just math. We just replaced X with W and Y with L. It still works. So let's do exactly that. Our goal is to predict values of Y that are as close as possible to Y hat, the correct label. What do we mean by close? We're going to do that 2 norm again, so Euclidean distance, and we're going to take the square to cancel out the square root. We don't care about that. And we're looking for a W, our model parameters, our model weights, such that this gets minimized for every Y. We can replace our prediction Y hat with this XW thing. So now our goal is to make sure that XW is close to Y. We can compute the gradient of this, which is the multidimensional derivative, set it equal to 0, and solve for W. So if I take the gradient of this thing, this is where you kind of have to trust me. If you have time and you're actually into math, this is a really good step to do as homework later, just to prove to yourself that this is true. But if I take this vector notation, I write it all out, and I take the derivative of it with respect to W, this is what I get. I get a matrix X transpose times X W star is what we mean by our optimal value of W, minus Y will equal to 0. I can do some quick matrix algebra and multiply both sides. I can distribute the X transpose through the parentheses and then subtract Y X transpose to the other side. I can take the inverse of X transpose X on both sides, and now I have a equation for W. This is really, really nice because all I need to know is X. If I know X, I know X transpose. That's easy. And you've probably, if you've taken linear algebra, you've done matrix inversion before. So that's X transpose X inverted. And you just multiply those three X's together, and now you know the optimal value of W for any Y. This is known as an analytic solution because I can just compute this. I don't actually have to do all of the steps of gradient descent. I know what the answer is. So this is linear regression. If you ever computed a line of best fit, this is the math that it's doing. Again, you don't have to understand this, but if you do, it's really powerful and it helps avoid certain mistakes of understanding whether or not the data needs to be normalized or other things that I'll talk about later. Okay. Now, earlier in lecture, I said all of these models can be used for classification, regression, etc. Linear regression has regression in the name, and we've done regression with it. So that's obviously a good model for regression. Can you do classification with linear regression? Of course, why not? So I can say all of my predicted values are either positive or negative. And my goal is to predict the sign of this formula. If I predict a positive number, it's in class 1. If I predict a negative number, it's in class 2. Easy, that's it. So if I just add this little sign function around my function, now it has become a classification model. The problem with this is it's kind of shit. It doesn't really work. So I'll show you an example of what I mean. Imagine you have the image on the left, where all of your blue data points belong to one class, and we're representing them as -1. All of my black data points belong to a different class, and we're representing them as +1. And they all happen to have different X values. This is really easy because basically anything greater than 0 is positive. Everything less than 0 is negative. So we can very easily separate our data. The problem is if I collect more data and I try to fit a line to this, all of a sudden that boundary shifts, where some of my black data points are now being incorrectly classified as the blue class. This is a really easy problem to solve. If we can't even solve this, then we're not really doing very well at classification. We're not even thinking about the case where some of the data points have the exact same X, but different values. There's a lot of noise in real data. So what we can do instead is we can use a different function. Ideally, we would like a function that doesn't really shift so much just because of outliers in either direction. One of the earliest functions that people in mathematics realize works well for this is a logistic function. There's actually many different kinds of logistic functions, so we'll use one of this specific form. And we're going to use log of 1 plus e to the -y wx. So the -y wx, you've seen that before. That's the y value, the weight, and the input. And then we're just making that an exponent and adding 1. If I try to take this function, I calculate the derivative, I set it equal to 0. There isn't like an easy solution. You can't just like convert things, move things to the other side and solve for solve for W. So there's no analytic solution for this. The only way to use this is gradient descent. So we would still take the derivative, we'd still take the gradient, but instead of setting it equal to 0, we try a bunch of random values and we go downhill. So imagine, again, we're in W1, W2, and error space. There is no X or Y. We don't care about X or Y. We care about W. We want to find the best value of W that minimizes our error. Now, if I show you this pretty surface, you can tell where the bottom of that is, but we don't know this ahead of time. We have to try a value of W1, W2, and see what the value of error is. So what we do with gradient descent is we pick a random initial value. In this case, W1 would be 7, and W2 would be -2 or so. And we would calculate the error and calculate the gradient of the error at that location. And we would say, okay, I know where I am, I know what my error is, but if I go this way, error decreases. So let's go this way. Let's try a different value of W1 and W2 in the direction of the negative gradient. How far do you go? Who knows? We haven't figured that out yet. So we're just going to go a certain ways. We're going to try again. Exact same thing, calculate the error, calculate the gradient of that error with respect to W1 and W2. We get a new gradient and it says to go this way. So we follow it and we keep doing that over and over until we go downhill and get to a local minimum. And that's how basically everything else for the rest of the semester will be done. Everything in deep learning is this. Everything in machine learning is basically this. So if this makes sense, great. You're done. You've graduated. You've learned everything in machine learning. You can play around with the model and make the model, the function, fancier, but you're pretty much always using gradient descent to learn the minimum, to optimize the function in that optimization process that is learning. Okay. One other thing that I want to talk about while we're on the topic of classification. Every example I've shown you so far has two classes, positive and negative. What would I do if I had more than two? There's actually a really funny YouTube video. Has anyone seen a show called Silicon Valley? No, this is an old show. Maybe I'm old. Let me show this, and this should explain what I'm talking about, and hopefully it's clear why I picked this video.
Please, God.
What will you say if I told you there is an app on the
We're
market?
past that part. Just demo it.
So for context, these people live in Silicon Valley. They are startup people. The guy who was just yelling, he's like the incubation head. So he's trying to teach these people how to make their own products and how to be successful business owners. And this guy came up with a new product, a new AI product that he's excited to present to them.
Let's start with a hot dog.
And ChatGPT.
Huzzah! Jinyang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Let's do pizza.
Yeah.
Pizza. Pizza.
Not hot dog.
Wait, what the fuck?
That's it. It only does hot dogs.
No, and a not hot dog.
Give me that. Give it to me.
So this, it turns out, is exactly how The vast majority of machine learning worked for decades. If you have a model that can do positive or negative, if you have more than just two classes, just add another model. If you build one model that can predict hot dog and not hot dog, another model that can predict pizza and not pizza, and just do that for all of the classes. If it's not a hot dog and it's not a pizza and it's not a cheeseburger, then it must be the fourth class that we care about. This is known as a one versus rest strategy. So it's either in this class or not. You can also do a one versus one strategy. So you can have a model that says it's either hot dog or pizza, another model that says it's either pizza or cheeseburger, etc. And you just look for agreement between all of these different models. So for the vast majority of history of machine learning, this is how we did multi-class classification. It seems stupid, but it works. And if it works, don't change it. When we get to deep learning, one of the things about deep learning that made it so attractive was that it could do multi-class classification directly. So it's not just predicting one number, it's predicting many numbers. And you can choose the number with the highest probability, and that is your answer. But at the moment, for this point in the classical machine learning space, this is usually how people do multi-class classification. There's one other supervised model I want to talk about before all of your brains explode, and that is a support vector machine. This is probably the most powerful classical machine learning model that you can get. If you look at any of like the machine learning competitions, this was really the last model that succeeded before deep learning kind of defeated it. So this is one of the most powerful models that you can use for simple machine learning tasks. So let's say we've got a bunch of data points. Again, we're back in X1, X2 space. So given some latitude and longitude or height and weight or whatever two features we have, we've got a bunch of points. And these points are classified into two different classes. There's a black class and a white class. Now, if we're doing classification, we want to learn a mathematical function that separates these two classes. If it's above this line, then it's one class. If it's below this line, it's a different class. There are many possible lines that we can learn. So you could pick H1, H2, H3. H1 is quite bad because one side of the line has one class, but the other side of the line has both classes. So that's not really great. We haven't really correctly classified these data points. But H2 and H3 are both perfectly valid. They, with 100% accuracy, correctly divide these two classes. We could use either one of these lines or functions to do classification. Which of those two is better? You don't have to use any fancy math skills. Just from your head, is H2 or H3 better? Why H3? What do you mean error? They're both 100% accurate.
I think for H2 to work, could only allow scattering across the x-axis, and the other way around, you have some more scattering in both directions.
Okay. The axis isn't super important, but the scattering is. So if I have data points here, real life data has noise. You will always find someone who has a little bit more X1 or a little bit less X2. And so if that's where the data points we know are, we should expect more in the general vicinity. H2, the line is really close to some of our data points. H3, we've actually maximized the distance between the line and all of our data points. And this is the entire idea behind support vector machines. Why are they called support vector machines? They're called machines because they're computers, and back in the day, everything that was a computer was a machine. Vector, well, that's the line we're learning. We're learning some vector line that separates these two classes. And support refers to these data points here, the data points that are closest to our line. So these dashed lines, these are called support vectors. There's two of them, one for each class. And our goal is to learn a W such that we maximize the distance between these two lines. This distance can be represented as 2 divided by the magnitude of W. And we can maximize this just by doing gradient descent and adding a negative sign, right? So just do gradient ascent, same thing. This works really well and with a lot less noise than some of our previous models. But it only works if the data is linearly separable. So in this previous example, all the blue points are on one side, all the green points are on the other side. Great. What if we mix up all the points? So there's not like one line that you can draw to separate the two. There's a couple different ways to do this. Some of the fancier things will change the function. You can also change the data. So what we're doing here is we're taking our input data in x1, x2 space, and we're actually warping that data to make it linearly separable. So now we're in x1 prime, x2 prime, a different space. This is done using something called a kernel, and there's many different kernels that you can choose from. Linear kernel, that's not really going to work unless it was already linearly separable to begin with, but I can use a polynomial, a sigmoid. The one that tends to be most popular and where I would start if I were you is this radial basis function, RBF. This is flexible enough that it can learn most warpings without adding too much noise. So this is how you can do support vector machines, even if your data is not linearly separable. So we're at a good stopping point. I want to give people time to use the restroom or clear their minds. So let's meet back in 8 minutes. So 4:25. Does that sound good? And I'm happy to answer any questions while we wait or look at Python install errors or whatever.
Ask about the Jupyter notebook. We just have to run it, right? Nothing. Okay, because
And then save the output so I can see it.
yeah, I tried opening it as a text file and everything was there. No, just to check if everything was there and it said properly. Is that fine then?
Yeah.
I just ran it and then uploaded that file.
Yeah.
Yeah, okay.
Yeah, I mean it's not a text file, but like it technically is a text file. Like
Yeah,
you
open
can
it with a text editor. That's
yeah. So you'll get like a JSON
Yeah,
structure
yeah.
and you can see the things in there. Yeah, that's all.
Yeah.
That's
Okay,
Yep.
I use that to check. Okay,
Yep.
great, thanks.
I had one question because I emailed you about
Yep.
the issue with the dynamic library.
Yep.
And you answered me that I could either globally do it for my ZHS, and I did that. And the other thing you mentioned is when I would configure my building thing, I use another CMake command, right?
Mhm.
And that links it correctly.
Yep.
Okay, got it.
Yeah.
Thank you.
Yep.
like in the last exercise, we had to install Pythons and all. On the last credit, I couldn't do that thing, like installation of GDAL. Could you help me out with that? Like how to do that?
Yeah, so I'll make this announcement for everyone. So for all the homeworks, all 11 or so homework assignments, there's the main part, like the 100%
Yeah.
part. I want to help you as much as I can with that to make sure everyone solves that. For the extra credit, I typically don't help much with the extra credit because that is like basically the challenge part.
I see.
So I won't give you too many hints on that part. A couple of people did basically solve it and had one bug at the end, so I offered advice on that. But for the most part, I want to let you try to see how much you can do without my help on the extra
I
credit
see.
things. Some of them are easier than others, so I think this one, if you find the right documentation, it's really easy, and if you don't, it's impossible. I've done it many times on Mac and Linux. I think it can be done on Windows, but I haven't tried. And then like for the next homework assignment today, I think you'll see that this one's a little bit easier for everyone to do.
Right.
So don't feel like you have to do the extra credit. If you are busy or you don't know how to do it, that is fine. You don't have to do it. But if you're bored and you want an extra challenge, do the extra credit and it will make up for any points that you lose on other assignments.
I see.
Yep.
Just one more question about citations. If we find any documentations, do we just like is it enough to insert the URL, or do we have to make a classical scientific?
So for code, just URL, just a little comment, I got this idea from here. That's fine. For the project, then you have to do like the classical citation, like Stewart et al. 2025 or whatever. And I'll show you how to get those pretty easily. One more minute. The first time I gave this lecture, I think it took like 3 hours because there's just so many models that you could try, so many different ways to explain it, so much math. But I've kind of simplified things to be what I think is actually important. Do people celebrate Halloween here? Is that a thing? Okay, good. Halloween is like the best holiday. Free candy. All right, 4:25. So let's get started. We've got about 30 minutes left, so let's start strong. Let's finish the last portion, which is unsupervised learning. This is your clustering algorithms mostly. Okay. So the basic formulation, the basic problem where you would want to use unsupervised learning. You have a bunch of data, you don't have any labels. You can pretty much always find data. You can find images, text. There's infinitely many data. Labels are much harder to come by. That requires someone, usually an expert, like a scientist, going in and labeling individual images themselves. That's really time consuming. It's really expensive. The vast majority of the time, there is much more unlabeled data than there is labeled. So can we use this unlabeled data and still get something useful out of it? Basically, can we find structure in this data? There's many different ways to do this. The way I want to focus on for the next 30 minutes is clustering. So the idea of clustering is to take all of our data and basically partition it into clusters. So assume that every data point belongs together with another data point. There's a bucket for cats, there's a bucket for dogs, but there's no bucket for both or neither. So we want to put our data in clusters. We don't really know how many clusters there are ahead of time, and I'll show you how to figure that out. But basically, we're going back to this idea of if the inputs look similar, they're probably similar. If it looks like a duck and it talks like a duck, then it is a duck, is the other phrase that people use. So similar things, group them together. Dissimilar things, push them apart. Simple. The most common way to do this, and you may have even seen this before, is something called k-means. One of the things that I notice is every time I introduce k-means, people see the k and they say, oh, it's just k-nearest neighbors. These are completely unrelated concepts. They both have a k, but other than that, they're quite different. So k-means, we're also looking at distance as a measure of similarity. But instead of memorizing every single data point, we're trying to learn an example, an exemplar, one data point or one general representation that represents a bunch of data points. So instead of memorizing every single data point, we memorize 4 or 5 data points and look for things similar or dissimilar to that. K-means is known as hard clustering. I will later talk about soft clustering and what that means. But here is an image of k-means. So I've got a bunch of data points in black. I don't know what they are, but some of them are close together and some of them are far apart in distance and space. So I can make clusters, that's these white X's, and everything that is closest to that one white X belongs to that cluster. So this kind of looks like that Voronoi diagram we saw before with k-nearest neighbors. That's maybe another reason why people get confused. But here we're learning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 clusters. We're only learning 10 data points. We only store 10 data points in memory. We don't have to memorize our entire data set. If I get a new data point right here, I can compare it to these 10 data points and say it's closest to this one, therefore it's that class. So similar idea, but much smaller memory footprint. It can't learn as complex of a structure. It's making some assumptions about the data distribution, but it works really well for clustering. And we don't need to know the answer. We don't know the answer for any of these data points, but we can say this data point is most similar to these other data points, and we learned a new cluster. The other thing that's special about k-means, these white X's, those may or may not be a real data point at all. So you can either learn a real data point that represents the ones near it, or you can just learn the mean, the center. And that mean represents all of those data points, even if it's not a real data point we've seen before. Those are both valid ways to approach k-means.
How do we actually draw the limits between the different clusters?
How would you learn the X's, or how would you draw the lines?
So basically the lines that separate the different clusters from each other.
So you can basically, for every point in space, compare it to those 10 points and see which one is closest in space. And if it's closest to this one, it's the same color as this one.
So basically the X's are predefined.
The X's are learned. We're doing machine learning. I'll teach you how to find the X's, but once you know the X's, then this should be easy. So how do we get these X's? We've got a bunch of data points, X. We don't have a Y, but we have hundreds or thousands of X's. And we would like to learn K centroids. That's the K and K-means, K clusters. And those clusters are going to be represented by a centroid, a mean value, mu. And then every point X belongs to a cluster C. There's K of those clusters in total. Any one cluster will be Cj. And there's n data points in total. Any one data point is xi. Hopefully that's not too many subscripts. Machine learning is the only place where I've seen subscripts with subscripts and superscripts with superscripts at the same time. And that's why machine learning math kind of scares me. But I didn't do any of that, luckily, so it's not that bad. Okay, so we have a summation here. For every data point, I equals 1 through n, the goal is that that data point, xi, is in cluster muj such that we minimize the distance between them. So which centroid mu is closest to this data point x? That's all that this means. It's just a really ugly mathematical way of writing it. I don't like math, if you can tell. Okay, so how do we learn these clusters? The first person who really invented most of the math behind k-means is this guy, Lloyd. And he came up with this idea called Lloyd's algorithm. It is an iterative algorithm. Step one, guess, as most people do when they don't know what they're doing. And then step two, do these two things over and over until it stops. So first, we've guessed k random data points, k clusters. They could be existing data points, or they could just be random points in space. It doesn't matter which. Step one, calculate the center. So all of our, actually, I think A and B should be flipped, but it doesn't really matter. Let's do B first. Let's assign all data points to one cluster or another. So for every data point xi, find the muj it is closest to and put it in Cj. It's in this cluster. And then the other step is compute the center of that cluster. So recompute muj based on this cluster. So if you imagine a bunch of random data points and you just pick one of them, if you fit 3 or 4 data points in there, the middle of that is going to be different than where you started. So keep iterating. This is much easier to visualize. So I have an animation here. So these 3 black stars, those are our cluster centroids. At the beginning of this animation, they're in 3 random places. 2 of them are in that top cluster, and then one of them is just in the middle of nowhere. And then during every step, we assign all of our data points xi to one of these 3 clusters. And we calculate the center of that cluster. And if we do those 2 things over and over, eventually, we usually learn good cluster centroids. It kind of feels like magic, but it's really just 2 steps and do it until it stops.
So we have to predefine the amount of centers or clusters.
Yes. In 2D, that's easy. You can just look at this and say, it looks like 3 clusters to me. So it's not hard to do this in 2D. In 10D or 12D or 1 million dimensional hyperspace, you can't visualize this. You can't really guess how many clusters there are. So I'll teach you later how to pick the number of clusters. But at the moment, pretend that you guessed and you got lucky. So if we guess the number of clusters and we're lucky, this method usually works well for our data. I say usually because nothing's perfect. So there's a lot of problems with k-means. It's really, really sensitive to the initialization. So when we pick our random cluster centroids at the beginning, if we get unlucky, it gets like stuck forever. So you might be in a situation where 2 cluster centroids are just right next to each other and they never really move because the means don't really move that much. So it's really, really sensitive to the initialization. There's a couple ways that people have gotten past this. One of them is to guess again, but guess multiple times. And if 9 times out of 10 you get one really nice looking cluster, and then 1 time out of 10 it sucks, don't use that one. Easy. So that's the brute force method. The other approach that people do is something called k-means plus plus. And this is basically a more clever way of distributing your data points. So none of them are too close together. And that's the slightly smarter way. But both of those are okay for overcoming this. They're not perfect. Another problem that we have is each point only belongs to one cluster. What if you have two clusters that are right next to each other? You have one data point in the middle. Which cluster does it belong to? At the moment, we have to pick one, which realistically, it could be both. It could be a little bit 50-50, different percentages of both. So ideally, we would actually represent it with some sort of probability of being in each cluster. Another big problem of k-means and a lot of these distance metric-based approaches is it's making this Gaussian assumption. It's assuming that every cluster is spherical, that distances are measured in Euclidean space, and if your clusters aren't spherical, this doesn't work anymore. And real data is never perfect. It's never a perfect sphere. It's never a perfect Gaussian. So we would like to be able to overcome that. Here are a couple examples where this kind of doesn't work. So here we have 3 clusters, and instead of spheres, they're more like ellipses. And k-means labels it like this, very confidently, of course. It says, yeah, that's a green cluster in the middle and an orange cluster and a blue cluster on the 2 diagonals. That's not really a good clustering. As humans, we can see there's kind of 3 lines, 3 ellipses, but the model can't do that because it's measuring distance the same in every direction. It also assumes equally sized clusters. So here we've got approximately 3 clusters. The one all the way to the right is really small and tight. The one in the middle is big and branching out for quite a large area. But when you do k-means clustering, all of your clusters end up having the exact same size because distance is the same regardless of where your starting point is. So these are some of the places where k-means doesn't work very well. So you can tell by the title of the slide, there's a fancier model that has some of the same ideas, but resolves many of these problems. It's called a Gaussian mixture model, or GMM. Instead of learning our cluster centroids, instead of learning one point that represents our cluster, why don't we learn a Gaussian distribution? So not just a point, but also a standard deviation. Here we have a mu j, this could be some vector, and then we have a sigma j that is a covariance matrix. So now our clusters can be any shape we want because they can have a Gaussian distribution around them. That distribution can be a different size, but it can also be a different shape if your matrix is not diagonal. The other thing we'll change is that every point belongs to every cluster with some probability. So if you look at the image on the right, if you've got a point that's halfway in between orange and green, it might be 40% orange, 49% green, and like 1% blue. It could technically come from the blue distribution and just be a huge outlier. It's just unlikely. So this is how we've changed our formulation. It's now probabilistic. It's not hard clustering, it's soft clustering. We say with some probability, it most likely belongs to this cluster, although especially some data points on the edge, we can't really know for certain, and it doesn't really matter anyway. We still want to learn clusters without worrying about the details of the exact bounds of those clusters. So if we run GMMs on this same data, it solves the first one. Great, we've got some nice ellipses. It also solves the second one. We have clusters of different sizes. Here I've done hard clustering, so I've said it's definitely green, it's definitely blue, but we actually do know the probability for every data point, how likely it is to belong to different clusters. So that's also a thing that we can use. How do we do this? So very similar approach as k-means. First, we need to guess. One of the ways that people actually do guessing for this, which is kind of funny, is they'll use k-means first to get our initial cluster centroids. That's a perfectly valid approach to guess. You can guess with a dumber model and then use that as an initialization for a smarter model. So we're going to guess intelligently with k-means. If we want to force our clusters to be circles, we can actually just use a diagonal covariance matrix and make everything else 0. And then it will be spheres, but they can change in size. If you have every point on the diagonal be equal, then all of your clusters are the same size. They all have the same standard deviation in space. So you can basically approximate k-means by dumbing down your Gaussian mixture. It's just a more abstract, more flexible version of k-means. Okay. And then if this works correctly, if I step through this process, you can see the two-step process for every data point. Given my current cluster centroids, I can make a probability distribution function for those points belonging to certain clusters. And if I do that same two-step iteration process, it basically looks like this. And eventually we will converge to a solution where we're learning these Gaussian distributions with different standard deviations in different directions, different cluster sizes, etc. I won't go into the math for this because I had to do the math on a homework assignment in my machine learning course, and it was literally like a 10-page LaTeX derivation. It's really ugly. But you can technically do the math for this. Luckily, scikit-learn, the library we'll look at later, does this for you. Okay. Again, not perfect. It solves some of the other problems, but it still has times when it doesn't work. So for instance, what about a non-Gaussian cluster? So you could have a weird data distribution that happens to look something like this. As a human, I can look at the image on the left and say, oh, that's kind of like a little bullseye pattern. Maybe the inner ring is one cluster and the outer ring is a different cluster. But regardless of whether you use k-means or GMMs, there's no way you're going to be able to separate those clusters in that way because you're learning a center. And the center of both of those rings is the same. So you can't really easily separate those. Same with the two half moons on the right. I don't know when these kind of data patterns exist, but assume that real data is ugly enough that you will get into situations like this. So what we can do instead, a solution for these kind of weird data distributions, instead of learning examples, we can play a game called Connect the Dots. This is known as hierarchical clustering. You just look for things that are close together and connect them, and that's it. There's actually two different ways to do this, two different approaches. You can do agglomerative clustering, which is a bottom-up approach. Basically, every single data point is its own cluster at the beginning. And then you look for the two clusters that are closest together, and you merge them. And you repeat until you've got a good number of clusters that do a good job of representing your data. The other approach is the divisive clustering. That's a top-down approach. You start with one giant cluster and you split it up based on the farthest data points. You can imagine how these two different approaches will get you slightly different results, but they both use kind of a similar idea. Okay. So the question that we had earlier, how do we know how many clusters we have? If it's 2D, easy. If it's not 2D, we're kind of screwed. We don't really know. So as we've seen quite often today, the correct answer is guess, but try different values. So we can pick many different k's, and if you look at the sum of the squared distances, basically the error, you should notice a pattern. You usually get some value of k for which you can keep increasing the number of clusters and error will keep decreasing, but it starts to plateau. You start to lose the benefits of making more clusters. This is the elbow of the graph. This is how you should pick K. And hint, you have to do this on your homework assignment, so don't forget this specific plot. We will be doing K-means clustering on homework 2 next week, so don't forget this slide. So that works great for K-means. That also works great for Gaussian mixture models. What about for hierarchical clustering? How do I choose K? I don't. Problem solved. So this is also a completely valid answer for any question. You can just ignore it. What hierarchical clustering does instead is it builds this tree-like structure where all of my data points are distributed in space. Here I've just kind of rearranged them. It doesn't really matter which ones are closest. And the closest ones get connected first. So wherever these two data points are, they happen to be really close together in space. They are exactly that distance away. So the y-axis is real physical meaning. It's the distance between two data points. So if these two data points are closest, I'll merge them first into one cluster. The next data point that is closest to this cluster is this one. So I'll merge those two, and I'll basically just go up. And at the end of the day, now we have this tree that tells us the distance between everything. And so we can just decide after the fact to draw a horizontal line anywhere we want through this graph. So for instance, I could say, you know, these data points are all pretty close together, but once I get around here or around here, we're starting to plateau. We're starting to see there's actually not that many things near this cluster. This cluster is kind of unique and different. So we'll make this one big thing on the left one cluster, and this little one on the right, maybe two clusters. That's perfectly fine. This thing on the right is called a dendrogram. You can also think of it as like a phylogenetic tree if you've taken any biology courses. But yeah, it's basically just modeling all possible values of K. This one tree contains all values of K. You can choose K later at your discretion. You can change it without recomputing anything just to see different possible clusters. But of course, this takes up a lot of memory and space. Okay. We've talked a bit about distance. At the moment, we've just treated everything as Euclidean distance. There's many different ways of measuring distance. This is your linkage criteria. So if I get a new point in green, which cluster does this point belong to? There's two different ways, or 3 or 4 different ways that I can do it. The first one is called single linkage. So it's the minimum distance between all points. What is the closest point? It is blue, therefore it is part of the blue cluster. This is pretty simple. Average is very similar to k-means. Now we're saying, where is the center of that blue cluster? Oh, it's way down here. Is it closer to this center or closer to that center? It's actually closer to the center of the orange distribution. Therefore, let's put it in orange. So that will get you something like those spherical clusters. You can also do complete, which is actually the maximum distance between that green and any point in either of the two clusters. So that would be that arrow up towards the right. I need to grow taller or get like a stick or something. And then ward is another one where you're minimizing the variance of the data distribution, so a little bit more probability based. Which one should you use? I don't know. Try all of them and see which one works best. It really depends on what kind of data you're working with. Here are a bunch of weird random data distributions, different linkage approaches, and the results that you would get. So for those 2 rings we saw earlier, single linkage works great because you've got this natural divide between the 2 distributions. It also works really well for the second half moon thing. For our bunch of Gaussian clusters, it works horribly. Ward linkage actually works quite well. For those 3 ellipses, none of them really work that well. Use Gaussian mixture models instead. For the second to last row, it looks like average linkage and complete linkage and ward linkage all work pretty well because we have kind of spheres. And then finally, if you just got a bunch of random data, it's never going to work well. Good luck. Okay. I have bombarded you with models today. I've shown you like 20 different models. You might be thinking, which one should I use? Some of them are good for classification, some of them are good for regression, but most of them can be used for all of these things. So how do I pick one model that I can expect to work well? Scikit-learn, the library that we're going to be using for the first half of the course, actually has a really nice cheat sheet to help you pick which model you want to use. So just like our decision tree from earlier, you start at the start value. If you have less than 50 data points, good luck, you're probably not going to get anything to work, so get more data. But if you've got more than 50 samples, it depends on what you're trying to predict. If you're trying to predict a category, basically classification, if you have labels, go to this classification bucket. If you don't, go to this clustering bucket. Are you trying to predict a number or a quantity? If you have labels, go to regression. If you don't have labels and you're just kind of investigating the data, there are things like dimensionality reduction, like PCA. We're not really going to be covering that much in this course, but that is another form of machine learning that would work well. And yeah, if you're trying to predict structure, good luck. Scikit-learn is not for you. There's other packages for that. Once you get inside of one of these 4 buckets, it depends again on how much data you have. So if you're doing classification, if you've got less than 100,000 data points, which is probably what you usually have, something like linear support vector classification would work quite well. So that's the SVM that we learned. If you have more than 100,000 data points, SVM is just too slow. So you should use stochastic gradient descent with a linear model, and that's getting a little bit closer to the deep learning territory. But scikit-learn tries not to do too much deep learning. If you're doing regression, if you've got less than 100,000 samples, and most features are useful, then ridge regression, which is just a fancier form of linear regression, or lasso or ElasticNet if you expect a small number of features to be useful. But if you've got over 100,000 samples, then just use stochastic gradient descent. It's faster. So this is a useful cheat sheet. There's rarely one model that always works. So try multiple, but this would be good to tell you like 1 or 2 models to start from. The last thing I want to talk about is software libraries. So this is a platforms and best practices course. We're mostly doing applications. So the lectures are the math, but the homework is where you start coding and solving problems. There's a bunch of kind of fundamental data science Python libraries that we're going to be using in this course. Those include things like NumPy, which brings array data structures to Python, and has, basic linear algebra features. SciPy, which has more advanced science-specific things like statistics, optimization, linear algebra. Matplotlib, which is for plotting. Pandas, which is for table-like data structures. So the kind of things that you would do in Microsoft Excel, you can do in Pandas. And then scikit-learn, that's where you have a lot of the classical machine learning capabilities. So these are going to be the bread and butter of the next 5 or so weeks. This is what you're going to be using on most homework assignments. Homework 1, this week's homework, you're basically going to pick NumPy or Pandas and then use that scikit-learn and Matplotlib. I would personally recommend Pandas, but if you're not comfortable with Pandas, NumPy is a bit simpler. If you don't know these, if you haven't used these before, there is documentation for these. Don't read all of this. It's going to take you more than 6 months to read all of these. There's too much documentation. So know what these libraries are for, and that will help you with searching. So if you're trying to plot something, don't use NumPy. Use Matplotlib. And then you can say, how do I make a bar chart in Matplotlib? And that will get you there much quicker. and then read the documentation as needed. If you want to make a bar chart in Matplotlib, don't read all of the Matplotlib documentation, but do read the documentation or the tutorials on making a bar chart. Each week, I'll try to give you a reading list of things that I think are useful. These are completely optional, but some of these may or may not help a lot with solving the homework assignment. If you've never used pandas before, indexing, slicing into a pandas data frame is really complicated, but also really powerful. Read this user guide, and this will teach you everything you need to know. We are going to be dealing with time series data. Pandas has a lot of really nice features for dealing with time series, and you can read this user guide to learn about those. We're going to be doing linear regression. Scikit-learn has built-in support for linear regression. There's an entire documentation page and tutorial just on linear models. There's also one for scikit-learn for time series data, which is what we're going to be doing. There's even one specifically for CO2 data, which is what we'll be using. And then, yeah, read these as needed. You don't have to. They will take time, but they will also save you time if you read them first. So what is your homework for this week? I want to start with a quick history lesson. You've probably heard of this guy, Fourier, before. He's a very famous French mathematician. He discovered Fourier series, which is one of the reasons that everyone hates him, because no one likes Fourier series. It's too complicated. But it's really useful for a lot of things. So he developed that mostly for studying harmonic data and things like heat transfer, vibrations. So if you do engineering, his name comes up all the time. What you might not know is he discovered the greenhouse effect back in 1824. So he was the first person who noticed if I take a glass box and I seal it, the temperature increases. And if I have another box without a lid, the temperature stays the same. So he noticed that there's this weird effect where you can capture heat in a box, but he had no idea why. He just discovered that it exists, and that was way back in 1824. Then Eunice, an American scientist and political activist, way back in, I think is 1850s or so, she was actually the first person to figure out the cause of the greenhouse effect. So she did a ton of experiments on things like water vapor and CO2 and noticed that these kind of small molecules would actually cause temperatures to rise more than others. So if I take that glass box and I remove all the oxygen, you're not going to get a greenhouse effect. But if I add CO2, you're going to get even more of a greenhouse effect. If you add water vapor, basically clouds, you get an even stronger greenhouse effect. So that was way back in the 1850s, where we already knew what greenhouse effect was and we already figured out the cause. And then this is an interesting person, not only because he has part of my name in his name, but because he was not a scientist. He was a entrepreneur. He was an inventor. He was not a scientist at all, but he was an amateur meteorologist. And way back in 1938, he was actually the first person to discover global warming. So he would travel across the country to sell products, but he would also make measurements of temperature at all these locations. And what he noticed was it kind of seemed like this temperature is increasing over time, and the CO2 levels in the atmosphere are increasing over time. And so he presented these findings back in 1938, and everyone laughed at him because he's not a scientist. What does he know? He's got all these observations, these measurements, but it's not rigorous. There's probably a lot of noise in the data. The data itself is not good enough to make these kind of assumptions. How could temperatures possibly increase over time that would violate laws of conservation of energy? So everyone ignored him back in 1938. And then this guy, Charles David Keeling, who actually did his PhD the same place I did, started taking observations in the same place every single day for the rest of his life. And these were specifically at the Mauna Loa Observatory in Hawaii, because it's very far from humans. It's in the middle of the ocean. So if you take a high altitude weather balloon, you can make an observation there at the same time in the same place every day for years and find these kind of trends. So he started doing this in March of 1958. Even after he passed away, we've gotten funding to continue these experiments for the last 70 years. And this basically proved that CO2 is rising in the atmosphere over time. And since we know that CO2 is a greenhouse gas, that means the temperature should also rise. So I'll show you this figure in a second. This is known as the Keeling curve, named after him. And then also, before I forget, next week we're going to be talking about data sources, including how to download your own satellite imagery. I'm going to show how to do this with your web browser. Bring a laptop if you remember, and then you can follow along. If not, you can watch the video later and remember how we do it. But you'll need to do that for homework too. So that's useful. Okay, so let's look at two things. We have our Keeling curve. So this is run by UC San Diego and Scripps Institute of Oceanography. And this is CO2 measurements recently. So this is the last 7 days. They're measuring it like basically once per hour, but it wasn't always that reliable. And you can see both the hourly averages and the daily averages for the last 7 days. So the current, go back here, current CO2 reading is about 420 parts per million. If you've got a million molecules, 420 of those are CO2. The rest is oxygen and helium and hydrogen. Okay, so that's the last week. That's the last month. A lot of noise there, but you can do weekly averages. What if we go to the 6-month level? We start to see a trend here. So things are starting to change over time. If I go to 1 year, you start seeing this kind of sinusoid, and it becomes even more clear at 2 years. So what is this sinusoid? If you notice, the values peak in the summer, and then they rapidly decrease in the winter, specifically the northern hemisphere summer and winter. What they observed is in the summer, plants have leaves, they soak up CO2. In the winter, all of those leaves drop. They stop soaking up CO2, those leaves decompose, and that CO2 is released back into the atmosphere. So there's a natural seasonal variation in CO2 due to plants. That's perfectly fine. The problem is you notice that last year is a little bit higher than the year before. And if you look at the last 70 years, you notice this pattern. So CO2 used to be like 320 parts per million just back when they started measuring it. It's already at 420, just within a very short time span. So it's not doubled, but like it's getting close to doubling just in the last 100 years. So that's what really proved the rise of CO2. You might have also seen some of these other figures. So you can look back even before he started making observations at other people's observations. There's a little bit more noise, they're a little bit more variable, but you'll notice all the way back until the 1700s, CO2 levels were pretty static. It wasn't really until the Industrial Revolution that all of a sudden they started to increase. You can go back even farther by looking at different, what are they called? Proxy measurements, things like ice cores, things like tree rings, various things that will tell you an estimate of CO2, and you get this famous hockey stick curve. So it was relatively flat for 2,000 years. It's just in the last 100 years or so where things have exploded very quickly. You can go back 10,000 years and it becomes even more obvious that something is very wrong in the Earth's atmosphere. You can even go back 800,000 years, and you'll notice that there are a lot of changes up and down. But the current change is just so much faster than anyone expected to be possible that the the Earth's climate and all of the things that live on it can't really adapt to this rapid change. You can even go back 70 million years, and you'll see that CO2 levels and temperatures were much higher in the past. So it's not the absolute numbers that are bad, it's the rate of change. And that's why everyone is so afraid of climate change, because this is really unprecedented. The Earth's atmosphere has never changed this quickly, other than like the asteroid that killed all the dinosaurs. And we would hope that we are not currently killing all the dinosaurs, but unfortunately we are. So with that beautiful and happy motivation, your homework this week is to do regression on this healing curve data. So this is mostly the same as last week. This Jupyter notebook, you will download it, you will write your code in here, you will save it, you will run it, then you will save it. Otherwise, you don't know if it worked. And then you will upload it. And that way I can see whether or not you solved it. I can also run it myself to make sure it works. And yeah, save the output so I can actually see the plots you make. Otherwise, I have to run it. This is the curve. Okay, this is the other really important thing that I want to explain. For all homework assignments this semester, there are certain things that you can use, and there's certain things you can't use. There's a bunch of built-in stuff in Python. You can use that. That's like sys and time and date time and various low-level things. So you can use any built-in Python functions, any built-in Python modules. The only third-party Python libraries you're allowed to use are the ones that I'm using here. So you can use anything in NumPy, you can use anything in Pandas, you can use anything in Matplotlib or scikit-learn, not just the parts that I've imported. You could import something else from scikit-learn if you want to, but these are the specific functions that I imported to solve this homework. That is also a really useful hint. You might want to read the documentation for those functions because they might save you a lot of time. So step one, download the data. We're not going to download the entire time because it keeps changing every year, and I want to make sure that things are reproducible. That is an important best practice. So we're going to download this specific data set, Mauna Loa atmospheric CO2. It starts in 1958, and I think it goes until like 2005 or so. So it's like the first chunk of the data. You'll download it from this website and load it into a NumPy array or a Pandas data frame. Hint, it would be really cool if there was some built-in function to fetch data from OpenML with this name and load it into a Pandas array. It'd be great if you read the documentation, because for whatever reason, I do this little trick every year and no one ever uses this. They still manually download it and they load it with some other library. So you're not allowed to use SciPy, you're not allowed to use ARF, you're not allowed to use any of these other weird libraries. You're supposed to use these ones that I import here. So that will save you some time if you read the documentation. This can be solved with one line of code, very easy. Pre-processing. This is usually the hardest part of the process. We need to manipulate all of our data to get it in the right format. So you'll have columns for year, month, and day. Convert this to date time, so one shared format. Compute the day of the year, so 0 to 365, and then compute the sine and the cosine of that day of year. This is really useful for cyclic data, such as day of year, because day 365 is actually really similar to day 0 or day 1. They're much closer together than, say, day 200. So this is a transformation that we can use on our data to learn a nonlinear function. In this case, we're learning a sinusoid. I've got a hint here. The sine and cosine functions in NumPy assume radians, not degrees, so you have to fix that. And then another thing that always comes up here, I don't care about leap years. Yes, some days there's 366 days. 366 and 365 are basically the same number we can approximate. So don't worry too much about leap days and leap years, but someone always ends up writing some really complicated solution to fix that. I don't care. Then we train our models. So I'm actually going to make you train 3 different models. So we're doing linear regression, but we don't have to use the same data as input every time. First, just use that date time number. So this is your year, month, day. You'll have to convert this to a number, one number. Hint, there are some functions that can help you convert date times to numbers. But convert it to a number and just train a model on that number. And you should get basically a straight line. So to a first order approximation, you can fit this with a straight line. That's fine. Then I want to see what happens when you fit it to your date time, like you just did, and another number, the day of the year. You should end up seeing a zigzag, which is getting a little bit closer to this pattern. And then the third model, I want you to train with the date time, the sine of this day of year, and the cosine of this day of year. And then you should get a rising sinusoidal pattern. Using each of these models, which have been trained on data from 1958 to like 2005 or so, we basically fit a line to the data that we've seen before. I want you to predict the future. Specifically, I want you to predict the CO2 level today based on what we knew 15, 20 years ago. So predict the CO2 concentration for today, and then plot these. So I want you to plot the plot here for the data that you downloaded, so from 1958 to 2005. And then I also want you to plot the predictions of CO2 for the last 20 years. So using your 3 models, predict CO2 for the last 20 years and put all of them on the same plot. This is really important. Please label your plots. Please give it a title, label the axes, specify the units of CO2. Is it parts per million or parts per billion? This is really, really important for science. If you basically make something that looks like this with the same kind of labels, then you get full credit. But if you like don't label anything, it's really hard to share that with other people and do science. So do that. And then you might want to zoom in on your plot just to see one specific area, like the last 20 years. Then it's easier to notice some of these patterns. And then finally, answer some of these questions based on what you found. What happens when you use Model 2? How is Model 2 different from Model 1? How is Model 3 different from Model 1? Which one is best? The first time I said this, I wasn't very specific, and people did all these really fancy metrics to evaluate it. I just want you to look at it and tell me which one looks realistic. Using that model you chose for 3, what's today's CO2 concentration predicted? And how does this compare to the actual number that you saw here? So are we close, or is it rising even faster than we expected? And that's the homework. So this is really the first real homework assignment of the semester. It's not that hard, but if you've never done pandas before, if you've never done matplotlib before, it's really tedious, it's really annoying, and it's really frustrating. This is a really good weeding out assignment. If you struggle, but you are able to finish it, you'll probably be fine for the rest of the semester. There are harder homework assignments, but things get like a little bit harder every week, and you're reusing things that you used in previous weeks, so it's not that bad. If you can't solve this one, because like you've never done any NumPy or pandas before, or Python is like your third language, then you might decide like if you want to continue with the course, and we can talk. There are the resources that I shared, both the reading list this week and also that data science book that I recommended last week. Those are good places to start. But I think if you read those things in the reading list, this should be manageable by everyone. I've had people take the course before that didn't know any Python and they did survive. It just wasn't as easy. So this will get everyone on the same page. If you can solve this, if it's easy, great. If it's really hard, but you still solve it, perfect. That's fine too. So don't worry too much if this takes you a lot of time. But I do recommend starting soon, like this weekend, and then you'll have a couple weeks to figure out the details. If you struggle with anything, you can ask for help in the next lecture, or you can email me, or I also have office hours on Tuesdays, but it's way down in Ottobrunn. But I could make a Zoom link if I have to. So that's the homework. As usual, there's extra credit, completely optional. You can use it to make up for points that you lose on this assignment or any later assignment. And it's not too hard. Basically, we've done a linear trend. We've done a linear trend with a smaller linear trend every year. It's like a zigzag. And then we've also done a linear trend with a sinusoidal trend. I want you to do an exponential trend. The easiest way to do the extra credit, the only hint I'll give you, it really helps if you write down the math first and then try to write the code to match the math. So you kind of have to transform your data into this exponential curve space using either an exponent or a logarithm or something like that. So that's the extra credit. If you solve this stuff quickly in your board and you want more of a challenge, do this extra credit. If you struggle with this and it takes you 2 weeks, that's completely fine. Ignore the extra credit. Any questions on the homework, the lecture? I kept you guys a little late, so sorry. You can leave now. Enjoy your Halloween. And I'll see everyone next week.